Welcome back. So the last time we were looking at twice differentiability, and we saw that the mixed order partial derivatives need not be equal even if the function looks perfectly innocent otherwise, even if the function is C1. Yeah? So to remedy this, we will make a new definition. A function f from U to Rm where U is open, okay, let's say this is an Rn, is said to be C2 on U if the derivative, right, if first of all f is differentiable on U and the derivative when treated as a function from U to Rm times n, yeah, if the derivative is C1 on U. Okay? So in other words, what do we mean when we say C2? What we mean is the derivative, which is a function from U to matrices, of course, this matrix valued function, which when I take a matrix, I'll just arrange all the entries as a single vector. So this derivative is C1 on U. What does that mean? This is what does it mean for a function to be C1, especially a vector valued function? Recall that it means every component has partial derivatives, all of its partial derivatives exist. In other words, the derivative matrix of the vector valued function exists, right, the matrix of partial derivatives, and this matrix valued function is continuous in its own right. Okay? So if the derivative is already a function of this sort, we take a further derivative of this, meaning what does that mean? Or what that means, this means the following: all the partial derivatives dxi of dxj exist and are continuous. So all the partial derivatives of order 2, that means you take two partial derivatives in possibly different variables, they exist for all I and j, and each one of them is a continuous function. Okay, that's what C2 means. Now if this is C1, right, this means df is continuous, is differentiable, which means df is continuous. Yeah? So if a function is C2, that means if df is C1, which means the partials up to order 2 exist and they are continuous, then df is differentiable as a function, right? Because any vector valued function which is C1 is differentiable. And any differentiable function is continuous, which means f is itself, and hence f is differentiable, and hence f is continuous. Which means what? A C2 function is also C1. C1 functions are also continuous. Continuous is sometimes called C0, by the way. Some people call it C0 because you're not differentiating any time. This stands for differentiating 0 times. C1 means the first partial derivatives are continuous. C2 means the second partial derivatives are continuous, right? C0 means no partial derivatives, namely the function is itself continuous. So in other words, C2 implies C1 and continuous. Okay. More generally, inductively we can make this definition. F is CR on U if all the R minus 1th order partials exist, partial derivatives exist, and are C1. That is, partials up to order R exist, or order R exist, and the rth order partials, the partial derivatives, are continuous. Okay. Now, because the rth order partial derivatives are continuous, what does that mean? That means the r minus 1th order partial derivatives are C1, right? That's what this means. So because they are C1, the r minus 1th order partials are all differentiable functions. Therefore, they are all continuous functions, right? Which means the r minus 1th order partials are C1, and therefore you can keep repeating this argument. You can rinse and repeat and say that CR implies CR minus 1 and so on. So in other words, if you're CR, you are better than being CR minus 1. So a CR function is differentiable R times, and all partial derivatives are continuous up to order R. Okay? This is a little proposition. It's not immediate from the definition. It uses the fact that C1 implies differentiable and the fact that differentiable implies continuous. Okay? All right. C infinity is sometimes called smooth. Simply means that it is CR for every R. C infinity simply means partial derivatives of all orders exist and each of them is continuous. Okay? That's C infinity. It's the best possible thing there is. Okay? So that's called a smooth function. Right? Okay. So what's the point of defining C1? I mean C2 rather, right? The point, among other things, is this theorem due to Clairaut. So Clairaut's theorem is if f from U in Rn to R, this is open, is C2 on U, and then the mixed order partial derivatives d by dxi, d by dxj of f at A equals d by dxj, d by dxi of f at A for all I comma j and A. I and j of course belong to N and A in U. So if you're a C2 function, then the mixed partial derivatives are equal. So in other words, the example we looked at in the previous, the latest example we looked at of mixed partial derivatives not being equal, the real problem was it was not C2. But actually, even that is not completely accurate. It turns out if your function is twice differentiable, what does that mean? df, the function is once differentiable and therefore the derivative matrix exists, and the derivative matrix is also a differentiable function. If a function is twice differentiable, even then the mixed partial derivatives turn out to be equal. That is a much harder theorem to prove. That requires more work. Okay? So we will not bother with it because in practice, wherever we will use this result, our functions will be C2 anyway. Okay? It's hard to come up with examples of functions that are differentiable, but functions which have partial derivatives, but partial derivatives are not continuous. Right? They're very contrived examples as the one that we looked at earlier. Okay? So this is Clairaut's theorem, and we'll prove that this theorem. This is not a trivial theorem to prove. Okay. So the first order of business is to note the following. We are interested in only xi and xj. Okay. We are fixing the other variables. So without loss of generality, assume that f is a function of two variables. Variables x and y. In what sense are we not losing generality? We are fixing all the other variables, so define a new function if you prefer, g of xy as f of all the variables are fixed except for xi and xj, and I'm calling xi and xj as x and y. Okay. And we'll handle this. So the key idea here is to prove so we will prove a second order mean value theorem. Sort of like a Lagrange mean value theorem, but for second derivatives in a sense. Okay. So that will tell us what to do, right? So how does this work? So suppose you take lambda of h comma k, and this is f of a comma b minus a plus h comma b minus f of a plus b comma k plus f of a plus h comma b plus k. Okay. What we shall do is the following. We shall prove that lambda of h comma k is h times k times this one at some point, right? And it is h times k times f of this one, where P and Q are 2 points in this rectangle. So P and Q are 2 points in this rectangle. Okay. How does it help? Suppose you assume that this theorem has been, this proposition has been proven. Suppose you assume this. Assume this is true. How does that help, right? The way it helps is lambda of h comma k divided by hk is, let's call this fyx of p. This is fxy of q. Now as h comma k goes to 0, 0, right, p goes to a comma b, q also goes to a comma b. Why is that so? Because the coordinates of p are between, the x coordinate is between, for example, a and a plus h. So by the sandwich theorem, as h goes to 0, the x coordinate of p goes to a. Likewise, the y coordinate of p goes to b. Again, by the sandwich theorem, for q also the same reasoning applies. And because fyx is assumed to be continuous, in fact, are assumed to be continuous. Okay? That means that this goes to fyx of a comma b, this goes to fxy of a comma b, and therefore these two are equal. Okay? So that will prove our result. Okay? So essentially the intuition here is that you can interchange, so this is what is known as a second order difference, right? So you're taking f of a plus h and b and you're taking the difference between these two, okay? This is what? This is roughly speaking the derivative, partial derivative with respect to x times h, right? This is roughly speaking minus h times the partial derivative with respect to x. And this is what? This is roughly speaking the same thing. This is h times the partial derivative with respect to x, except that this is evaluated roughly speaking at a comma b plus k, and this is evaluated roughly speaking at a comma b. So the difference is roughly speaking the partial derivative with respect to y of the partial derivative with respect to x of a comma b, okay? And you can interchange the roles of a and b. So the point is, this is a second order difference, right? And for, if you don't take limits, right, the second order difference is symmetric in h and k, right? So the roles of h and k can be interchanged. Notice that if you interchange h, I mean, the same operations that are done for h are done for k, okay? So if you interchange the x and y coordinates, right, in some sense this is symmetric, right? So the same, so that is being leveraged here, okay? So we are taking a second order difference and we know that it behaves symmetrically in both variables, and therefore we prove some sort of a mean value theorem, and that's why these two are equal, okay? That's the rough idea of the proof. So let's try to prove this. This is the key point. Notice that if we prove this, then the same proof will be used to prove this, because whatever proof we use for this, you just interchange the roles of x and y and you will get the proof for this, okay? So let's prove this one, okay? And the idea is also right in front of us, right? It's basically making these approximations precise. If you want to get the other equation, then what you could do is you could then take this one and this one. If you compare this and this is approximately k times the partial derivative with respect to y. This is also approximately k times the partial derivative with respect to y, and you compare them, okay? So that's the idea here. So the idea, so let's put this idea into practice. So suppose phi of s is f of s comma b plus k minus f of s comma b. So this is a one variable function, yeah? So let's write lambda of h comma k in terms of this one variable function. This is phi of a plus h minus phi of a. Why is it phi of a plus h minus phi of a? Because that would mean it's f of a plus h comma b plus k minus f of a comma b. Are these terms there? F of a plus h b comma k minus, sorry, where is this? So yeah, f of a plus h comma b, right? So f of a plus h comma b plus k minus f of a plus h comma b. That is phi of a plus h. What is phi of a? Phi of a is this part, right? It's simply phi of a is f of a comma b plus k minus f of a comma b, right? Now you see where we are heading to, right? So using Lagrange's mean value theorem. Why is Lagrange's mean value theorem applicable in this scenario? The point is, f is differentiable with respect to s, right? So what would Lagrange's mean value theorem need? It would need the one variable function to be continuous on a closed interval, differentiable on the open interval, and so on. It's indeed continuous. I mean, f is C2, hence it's continuous. F is C1, hence it's differentiable. In particular, the partial derivatives are assumed to exist. So this equals phi dash of some theta times a plus h minus theta, a. So it is h times d by dx of f of theta comma b plus k minus h times d by dx of f of theta comma b. All right. So that's the first step, right? Okay. So this is h times d by dx of f of theta comma b plus k minus d by dx of f of theta comma b. Now this is again a one variable function. Theta is fixed, right? What's changing is only y here. We use Lagrange's mean value theorem again to conclude that this is k times d by dy of d by dx of f of theta comma, let's call it theta dash. Okay. So this proves that indeed lambda of h comma k is hk times d by dy d by dx of something. The same proof will show the other equality as well. Okay, so this is a slightly clever way of doing things. Naively what would we have done? We would have tried to make this exact by using the Lagrange mean value theorem at this level. Then we would have said this is h times the partial derivative of x with respect to a point theta 1 comma b. The trouble is when you play the same game here, the theta that you get is different from the theta that you get here. Okay? So you get two different thetas. So it's not as obvious as it looks, right? We are getting in one shot, we are able to handle this entire difference by treating this as the one variable function. In other words, we are not applying Lagrange's mean value theorem with respect to the x coordinate for two different functions. No, we are handling them as one single one variable function, and that is a slightly non-trivial idea. Okay? So it's not an immediately obvious theorem. Okay? This required a tad amount of ingenuity. Okay. Right. Okay, so that's great. So this proves Clairaut's theorem, but in fact we can do better proposition. Right. As a corollary of Clairaut's theorem, right? Corollary. If f is CR, then all mixed partial derivatives up to order r are equal. Okay. What does this mean? What does this phrase mean? If you take let's say a C5 function, and if I take, let's say, 4 partial derivatives, if I interchange their orders, I'll still get the same number. And this 4 is arbitrary. It could have been 5, it could have been 3, 2, or 1. Okay? I mean, there's nothing in 1, but 2. So 2 we've already proven. That's Clairaut's theorem. So 3, 4, and 5. Okay? So how does one prove it? We perform mathematical induction, of course. We induct on R. Right? So R equals 2, that is the base case, is Clairaut's theorem. So we've already proven Clairaut's theorem. Assume the truth of this proposition for 1, 2, so on until r minus 1. So what would that mean? That would mean if you take d by dxi of d by dx j1 so on until d by dx jk, right? In fact, I would say jr minus. So when you say the truth, assume truth for 1, 2, 3, so on until r minus 1, the point here is that if you have a CR function, as we saw earlier, it is also CR minus 1, right? So a CR function is automatically CR minus 1. So all mixed partial derivatives up to order r minus 1 are equal anyway. So the only thing that is new is looking at a mixed partial of order r, right? So namely things like this, okay? So if you want to look at these sorts of mixed partials of order r, right, what can we say about them, right? So this is CR, it's a CR function, which means if you take any order r minus 1th partial, it is C1. In fact, it's a bit more. If you take any order r minus 2th partial, right, it is C2. So this is C2. So we can happily apply Clairaut's theorem, that is the base case of the induction hypothesis, to conclude that this is actually equal to this times the rest. Okay? So we can interchange these two partial derivatives. If you treat this entire thing as a function, right, in its own right, we can interchange these two partial derivatives because this function, which I'm representing as a rectangle, is C2, right? Now what can we do? Now the point is, you can now take this d by dxi anywhere else inside, right? So you can permute I to any position in this partial derivatives, right? So what have we accomplished? We have shown, ideally we would want to say that this is equal to, if I choose some standard ordering of these things, let's say, actually maybe I won't say that yet here. I want to say that regardless of how you permute these, I'll get the same number, right? So far what have we proven? We have proven that this particular thing can be permuted to any position that we want, right? I claim that is good enough to prove what we want. Okay, why is that good enough, right? So the idea is, again, this is by mathematical induction, right, on the number of variables. This is just a question about permutations. So if you can permute this to any position you want, right, then what do? Suppose you take this and you want to consider some permutation of it. That means you want to rearrange these in some way, okay? Then this particular variable must go to some place, right, in the new permutation. So why don't you keep interchanging it till it goes to its correct place, right? Once it goes to its correct place, you fix its position, right? And then you can interchange the other variables. You can play the same game on the other variables and inductively bring them to their correct positions, okay? The claim is basically that this implies that we are done. The question is why, okay? This is simply an exercise in permutations, right? So I invite you to do this on your own, okay? How would you permute this to the correct place? The most systematic way of proving such a thing would be as follows. You can take I and you can put it in any place you want, right? So suppose you put it in some place, right? You can so suppose you put it in, let's say, this place. The claim is you can take this and bring it back to the position of where I was. That is, you can perform an interchange of two things using this process. How? You put I in its place, this will be somewhere. Since this function is CR minus 1, you can pretend that this is at this place, right? Because by the induction hypothesis, then you can interchange these two, okay? So please think about it. Please think about how you can interchange any two things. Once you can interchange any two things, then you can get any arbitrary permutation by a sequence of interchanges, okay? So this requires some amount of thought, but I invite you to think about it because this will give you some clarity on how Clairaut's theorem works, okay? I'm deliberately not giving you all the details, all right? So that's great. So we have proven a very interesting result here. So we will continue with this the next time. We are done with Clairaut's theorem, and the next time we will continue with proving a little bit more about the compositions of functions, and then we will proceed to other topics. Okay, thank you for joining.